Okay, today we will talk about hydraulic resistance of two channels connected in series, and we know that we can apply Pauli equation to find the overall pressure drop across two channels connected in series, and Pauli equation is valid when the Reynolds number are relatively small, so that the flow is laminar, okay, and uniform. When we have let us say a case where we have recirculation zones developing in a channel flow situation, we cannot apply Pauli flow or Pauli equation, okay. So we consider a case have two channels connected and we are going to find the hydraulic resistance. The hydraulic resistance, okay. So let us consider a case where we have a back step, okay. So let us say this height is h1 and this height here is h2, and the resistance of this segment of the channel is R1 and this segment is R2, okay. So here the pressure is P star plus delta P, and here the pressure is P star. So we have two hydraulic resistances R1 and R2 connected in series, right. So and that forms a back step, okay. So the back step height is h1 minus h2, okay. So we consider the first case, okay, where the Reynolds number is less than 1, okay. So in that case the Hagen-Pauli law valid. So we can write the overall pressure drop delta P will be equal to R1 plus R2 into Q, okay. Now so here if the Reynolds number is small, the streamlines will look like this, okay. And so on. Now if you consider the Reynolds number is greater than 1, in that situation we can expect, so this is the back step, when the Reynolds number is greater than 1, what we would expect is a recirculation zone forming here, right. So there will be a recirculation zone forming there, and in that case, so here we would have recirculation zone develops, and this is because when Reynolds number is greater than 1, we have large inertia compared to viscous forces, right. So, in that case we cannot apply Hagen-Pauli law. So, Hagen-Pauli law is invalid, right. So, in that case we cannot write delta P equal to R1 plus R2 into Q. Okay. So, use of Hagen-Pauli law to calculate overall pressure drop across a series of channels is only valid when the flow is laminar and the flow is uniform. Okay. There are no vortices present. So, in that case we can find the overall pressure drop by considering the individual resistances. Okay. So, now let us look at how the equivalent resistance will be in case of two hydraulic resistors connected in series and when they are connected in parallel. So, we consider hydraulic resistors in series and parallel. Okay. So, let us consider two channels first, two individual channels. So, this is let us say channel 1 and here the pressure drop is P star plus delta P and pressure is P star. So, the resistance is R1 and flow is Q1. So, we can write delta P, let us call it delta P1 equal to R1 into Q1, right. So, now we consider another channel which is a little bit wider and here we have P star plus delta P2 and here the pressure is P star, we have resistance R2 and flow rate Q2. So, we can write delta P2 is R2 into Q2. Now, if we connect these two channels in series, if you connect these two channels in series, this is what we will get, right. So, here the pressure will be P star plus delta P and here the pressure will be P star and here the resistance is R1, here resistance is R2 and we have Q constant. Okay. So, we can write delta P will be equal to delta P1 plus delta P2, right. So, delta P equal to R1 plus R2 into Q. So, R1 into Q is delta P1 and R2 into Q is delta P2. So, this will be equal to R into Q. R is the equivalent resistance of this network. So, we can write R to be R1 plus R2. Okay. So, when two hydraulic resistors are connected in series, the equivalent resistance is the addition of the individual resistances, right. So, now let us look at when the hydraulic resistances are connected in parallel. So, when they are connected in parallel, let us consider this case here. Okay. So, this is P star plus delta P, this is P star. So, that these are two channels, this is channel 1, this is channel 2, they are connected in parallel. This is R1 and R1 is the resistance and Q1 is the flow rate, here is R2 and Q2. So, we can write Q, the total flow rate is going to be Q1 plus Q2, right. So, we can write delta P over R is going to be delta P1 over R1 plus delta P2 over R2. Now, since they are connected in parallel, the delta P are equal. So, delta P equal delta P1 equal to delta P2. So, the equivalent resistance 1 over R is going to be 1 over R1 plus 1 over R2. Okay. So, the hydraulic resistances behave the same way as electrical resistances. When they are in series, the equivalent resistance is the addition of the individual resistances, and when they are in parallel, it can be determined as 1 over R is 1 over R1 plus 1 over R2. Okay. This is because the Hagen-Paschali law is similar to Ohm's law, where the pressure drop is equivalent to the voltage drop, the flow rate is equivalent to the current, and we can also say that current is charge per time, right. So, the charge Q is equivalent to volume, right. So, we can define another parameter called hydraulic capacitance, okay, which is equivalent to electrical capacitance, which is also known as compliance. Okay. So, we discuss a term called compliance. So, the Hagen-Paschali law is equivalent to Ohm's law, and so the pressure drop is equivalent to voltage drop in electrical circuit, and the flow rate is equivalent to current, which is I. So, this is nothing but charge per time, right. So, charge is equivalent to the volume, right. So, the electrical capacitance C is dq over dV. Okay. So, elemental charge divided by the elemental voltage, right, the change in the voltage, so which is equivalent to a term called hydraulic capacitance, or it is also known as compliance. Okay. So, compliance can be defined as compliance is denoted by C hydraulic is minus dV over dP. Okay. So, here we notice that there is a negative sign here, and the negative sign is because as the pressure increases the volume diminishes. Okay. So, the volume and pressure are inversely proportional to each other. So, there is a negative sign there. Now, compliance has importance in design of microfluidic system. If you are not talking about ideal fluids, all real fluids have some degree of compliance. Okay. So, they can be compressed to some degree. Also if you are talking about microfluidic channels with flexible walls, the walls that are not very rigid, or we talk about microfluidic circuits that have some kind of membranes in it. So in that case understanding of compliance is very important. Okay. So here we will take two examples and we look at how compliance plays a role in microfluidic circuits. So the first example we will talk about. So in the first example we will talk about a gas which is compressed by advancing liquid. Okay. So you would have a gas contained in a specific volume and which is interfaced by a liquid, and as the liquid is advancing at certain flow rate we would try to find out how the pressure inside the gas would change with time. Okay. So we would consider this situation here. Okay. So this is a rigid wall. So we are not talking about deformable walls, we are only interested in how the pressure is varying for the gas. So this is the gas, let us say at some instant the pressure is P and the volume is V. This is the liquid, okay, which is moving at flow rate Q, and this is the liquid. Here the pressure is P star plus delta P, and till here we say the hydraulic resistance is R hydraulic. Here we talk about rigid wall. So the gas is trapped here in this volume and it is going to be compressed by an advancing liquid that we see here. Okay. So the compliance of gas is large compared to the walls. Okay. So that is the assumption that we are making because the walls are rigid. So let us say initial condition we have pressure P star everywhere, the liquid as well as the gas they are at pressure P star, and the gas volume is let us say V star. Okay. Now as the liquid is going to advance, the pressure is going to change to P and V. Okay. And if you assume that isothermal condition, okay, so you can apply the ideal gas law. So you can say P into V is going to be P star into V star. So you can find V equal to P star V star divided by P. Okay. Now we can find compliance C hydraulic is minus dV over dP. Okay. So we can find it to be P star into V star over P square. Okay. Now if the change in the pressure is negligible, that means let us say P is not very different than P star, we can say the capacitance, hydraulic capacitance will be B star over P star, okay, B star over P star, and this is when pressure change is negligible. Right. So, at time t equal to 0, at t equal to 0, the pressure is P star everywhere as we told in the beginning. So, pressure is P star everywhere, and as pressure of liquid increases, so the pressure will change from P star to P star plus delta P, right. So, the liquid flow rate as pressure will change, the liquid flow rate would be Qt, right. So, Q will be a function of time. So, and this liquid flow rate would be nothing but the decrease in the gas volume. So, as we see here, as the liquid is advancing, the gas volume is going to reduce. So, the liquid increase in the liquid volume per unit time is going to be the same as the decrease in the gas volume per unit time. So, the flow rate of the liquid is nothing but the delta V over delta time t, okay. So, the negative sign is because the volume is reducing with time, okay. So, now you can write again Qt is going to be minus del V over del P into del P over del T, okay. So, this can be written as minus del B over del P into del P over del T, right, which is equal to minus del B over del P is nothing but the hydraulic capacitance. So, C hydraulic into del P over del T, right. Now, if you use Hagen-Paschli law, so this is what we found. If you use Hagen-Paschli law, you can relate delta P to be R hydraulic into Q, right. So, you can write delta P equal to R hydraulic into Q, which will be equal to R hydraulic into Q, you can write it as minus del V over del T, minus del V over del T, and so this you can also write it as equal to R hydraulic into C hydraulic into del P over del T, right. You can write it as del P over del T, right. So, this you can expand del P over del P into del P over del T, right, minus. So, this becomes the C hydraulic and del P over del T, right. So, what we see from here is that del P equal to 1 over, so del P, sorry, what we see here is del P over del T equal to 1 over R hydraulic into C hydraulic into delta P, right. So, you can say del P, right. Now, if we integrate, so we first take it to other side. So, del P into right. So, now if you do an integration, what you would see is P over time is going to change as sorry, this is going to be delta p, right, delta p. So, if you do integration, so you take time that side and delta p here, you get that p t will be p star plus 1 minus e to the power minus t over tau into delta p. This is what you would get. Okay. So, where the time constant tau is going to be R hydraulic into C hydraulic. Okay. So, this is the time constant, how the pressure is going to change with time. And if you look at this term, is very similar to the voltage across a charging capacitor, how the voltage changes with time in case of a charging capacitor. Similarly, the pressure is going to change with time. Okay. So, the Pt is similar to the voltage across a charging capacitor, where the Vt varies as V0 into 1 minus e to the power minus t over tau 0. Okay. So, if you have an electrical capacitor and you have a source, the charging also occurs in a similar way. Okay. So, the same fashion the pressure of the gas is going to change over time. Now, let us look at another example where we talk about a chamber with a flexible membrane. Okay. And we would see how the pressure of the chamber is going to vary with time. Okay. So, we consider another example of a chamber with a flexible membrane. Let us say this is the flexible membrane, okay, and this is the inlet, this is the outlet of the channel, right. Now, let us say the pressure here is P star plus delta P and the flow rate is Q1. Here let us say the flow rate is Q2 and pressure is P star, and so this is the deformed membrane. Let us say initially the membrane is at this shape, and let us say the pressure here somewhere at the middle is Pc, okay, and here the resistance on this part of the channel is R1 on the left side, and this is R2, and the volume rate here is Qc, okay, the rate at which liquid is advancing into the dead volume here, and this is a soft wall C hydraulic. Okay. So, we are considering here a soft walled channel filled with incompressible liquid, okay, and so that the compliance of liquid negligible, okay, is negligible. So, what we can write here is we can write the pressure is P star, right, at inlet, let us say for time t less than 0, and it gets to P star plus delta P for time t greater than 0. So, the flow rate at the inlet, you can find out the flow rate. So, when pressure is at T less than 0, when pressure is P star, the membrane is in the undeformed state, and when the inlet pressure changes to P star plus delta P, then the membrane keeps on deforming. So, the flow rate Q1 that is coming in at the inlet equal to P star plus delta P minus Pc is the central pressure divided by R1, right. And similarly, outlet, at the outlet you can write Q2 will be equal to Pc minus P star divided by R2, okay. So, from here you can find the rate of volume expansion, right, rate of volume expansion, which is same as the dead volume created here because of the expansion of the membrane, right. So, the rate of volume expansion Qc is minus del V over del T, and you can also write it as C hydraulic capacitance. So, you can write this as del V over del P into del P over del T. So, into del P C over del T, because the central pressure is P C, right. So, now you can write Q C equal to Q1 minus Q2. So, this is nothing but mass conservation, this is mass conservation. Q1 is what comes in and Q2 is what goes at the outlet. So, the difference is the volume expansion in terms of the expansion of the membrane. So, we can write Qc, we can write this, right. So, we can write del Pc over del T into C hydraulic will be equal to Q1, we have an expression for Q1 and also Q2, right. So, we can write P star plus delta P minus Pc divided by R1 minus Pc minus P star divided by R2. Now, if you rearrange the terms, you will get this del Pc over del T will be equal to minus 1 over tau 1 plus 1 over tau 2 into Pc plus 1 over tau 1 plus 1 over tau 2 into P star plus delta P over tau 1, where tau 1 will be R1 C hydraulic and tau 2 will be R2 C hydraulic. So, these are called hydraulic RC constants, okay, hydraulic RC constants. So, the solution would be Pc T will be P star plus 1 minus e to the power minus tau 1 to the power minus 1 plus tau 2 to the power minus 1 into T into tau 2 divided by tau 1 plus tau 2 into delta P, right. So, that is how the central pressure is going to vary over time, right, and this expression is similar to voltage across a charging capacitor which is charged by a voltage divider. Okay. So, if you look at an electrical equivalent, this expression looks similar to that. Okay. So, with that discussion we move on to talk about the drag force on a sphere in a liquid. Okay. So, we talk about drag force acting on a sphere in infinite domain. Okay. So, drag force acting on a sphere has practical importance in microfluidics when we talk about movement of particles or cells in microchannels. We would like to know what is the quantitative expression for the drag force that is acting on microparticles. Okay. So, let us consider this example. So, we have a sphere which is present in an infinite domain. So, say this is some r, this is theta, this is radius a. So, we would have the flow situation something like this. Okay. So, the pressure force always act normal to the surface, and there will be a viscous component tangential, right, and we are talking about uniform velocity u. So, we can write the free stream velocities, u r will be u into cos theta. So, this will be along the radius, and u theta is going to be minus u sin theta, right. So, we can write the governing equation. So, in this case we are talking about Stokes flow situation. In case of Stokes flow, the Reynolds number is less than 1. So, the Navier-Stokes equation reduces to something like a Poisson equation, where we have pressure gradient related to the viscous force. Okay. So, here we would have delta P equal to eta into del square u. Okay. So, this is nothing but the Stokes equation. Okay. So, here we can write down the boundary conditions. The boundary conditions are u at r equal to a equal to 0, and so that is the no slip, and the other condition is u at r tends to infinity is going to be u, that is the free stream velocity, right. So, there are different ways to calculate the velocity fields. Okay. So, which can be different mathematical techniques can be used to calculate the velocity fields. One approach would be to expand the velocity in terms of the ratio between the radius of the circle divided by the radial coordinate. Okay. So, one approach the velocity components in terms of power series in A over R. So, we can write down the velocity solutions in power series, UR will be equal to U cos theta into 1 minus 3 by 2 A over R plus half A q over R cube, and we can write U theta is going to be minus U sin theta into 1 minus 3 by 4 A over R minus 1 by 4 A cube over R cube. So, if you look at these two components, and you will see that these satisfy the boundary conditions. Okay. When R equal to A, both these components will vanish, and if you use the condition R tends to infinity, the velocity is going to be the free stream velocity, right. So, now if you plug these two solutions for the velocity in the Stokes equation, you can find the pressure expression. So, you would find the pressure I am writing is as delta P, okay, is equal to minus eta into U into 3 by 2 A over R square into cos theta. So, this is the pressure field, right. So, now if you want to find out drag force per unit area, you can find F drag, let us say per unit area, use the dash symbol, equal to minus cos theta. So, that makes it normal to the surface into delta P, right, minus sin theta into eta del U theta over del R. So, essentially this is the stress that is coming because of the fluid pressure, and if you take a cosine component, that becomes normal to the surface. Okay. So, this is the stress due to pressure, and this is the viscous stress. So, this is normal to the surface, right, this acts normal, and then you make cos theta. So, that makes it the component along the drag, and then this is tangential. Okay. So, you can find so that if you can substitute the value for the pressure, so this minus cos theta into the delta P that we see here into eta minus eta U cos theta into 3 by 2 A. So, this has to be evaluated at R equal to A at the radius. So, 3 by 2 A over R square, we had A over R square. So, that would be A over A square minus sin theta into, you have to take the gradient of the theta component of the velocity here, right. So, if you do that, you will get minus eta U sin theta into 3 by 2 into A over A square. Okay. So, then you can write this as you can write this, if you simplify you can write this the drag expression will be 3 by 2 into eta u over a. Okay. So that is per unit area. From there you can find the total drag. Total drag is going to be the drag for unit area into 4 pi s square. Okay. So, what you will get is 6 pi eta u a. Okay. So, the drag force is 6 pi eta u into a. Now, this expression for the drag is derived from the velocity components which are not valid at large distance from the sphere. Okay. So, if you look at these velocity components as r increases, okay, so the velocities ideally should become free stream velocity. So, but that is not happening, so that needs some corrections. So, the expression for the drag has been corrected by Oshin in 1910, where he said that the drag is going to be a function of the Reynolds number. Okay. So, the drag f d is going to be 6 pi eta u a into 1 plus 3 over 8 into Reynolds number. Okay. Now, we have looked at the expression for the drag assuming that the sphere is stationary. Okay. If the sphere is moving, then what would be the expression for the drag force? So, in case of a moving sphere, let us say it moves at some velocity u p, then the drag force f d can be written as 6 pi eta a into u minus u p. Okay. So, this is the velocity of the fluid and this is the particle velocity. Okay. So, with that let us stop here.